Well, hello everyone. Welcome to VizMath Session 7, and I'm Betty Hurley-Das-Gupta. I'm here with Carol Yeager, co-facilitator of VizMath. And very happy to welcome Brian Clare, who is going to be talking about Escher and the impossible. So thank you, Brian, and you can go ahead and put on your video if you want to.
All right. Hello, everybody, and welcome. I've been following VizMath for the last couple of months, and it seems like it's been a great project to be associated with. So I'm glad to be here to tell you a little bit about Escher and the impossible. I do need to apologize a little bit in advance. Some of the slides we're using are going to be a little messed up, so we may have to momentarily pause while I load up pictures that didn't make it in, but otherwise it should be good. All right. I'm going to give just a little brief thing about Escher as a person. He was a Dutch artist, so he's born in Holland, and he did the bulk of his well-known work from the late 30s, mid to late 30s, up until, really he worked until his death in 1972. He's primarily known as a graphic artist as opposed to, say, a fine artist, which is a distinction maybe the art world cares about more than the public. But generally what that meant is that he's working with prints, so he's making woodcuts and lithographs, and he was also taking commissions and doing work for commercial venues. So on this slide, there's a picture of him, and then there's also this. Let me see if I can point to it. There, practicing with my pointer. There's also this is a picture of a woodcut for one of his works called Smaller and Smaller. And you can see that to make a print, what he has to do is carve one of these wooden blocks, apply paint to the block, and then the levels that he didn't carve out, the raised level, will hold the paint and print it when it's pressed on the paper. So this was one of two different blocks he had to carve for this print. The other one gave the detailed black line outline. This would be the color orange block. So that's a little bit about Escher. I'm going to tell you a little bit about me as well. I started teaching at St. Louis University in fall 2000, and almost immediately after I started, I went into collaboration with Dr. Annika Bart, who's another professor here, and we developed a class called Math and the Art of MC Escher. And it's a one semester long course for freshmen, mainly freshmen, and they're generally students who didn't like taking, say, trigonometry or pre-calculus in either college or high school, but need to take one more math course, and so they'll take our Math and Escher course. And we do a lot of really interesting math. It's based off of Escher's work for the most part, and it's supposed to be sort of comparably hard to, say, a college algebra course without requiring years and years of background mathematics that most of the students in that class have not succeeded at. So it's been pretty popular. It's still running now, a little over a decade later. Okay. So in the course, there's really two main mathematical topics we do, neither one of which I'm going to talk about today. One of them is tessellations, which is a sort of a classical mathematics course component for a lot of these liberal arts math classes. So this is Escher's Day and Night. It's one of his earliest well-known works, and in it you see that there's sort of two interlocking types of bird. There's black birds flying left, white birds flying to the right, and at least in the middle of the picture, there's no space between them. So these birds tessellate the plane. They fill it out with no gaps. Hi, Kelsey. This print shows one of Escher's sort of main artistic themes, which you can kind of keep your eye open as we look through his work. One of his themes is duality, and so in here there's this left and right symmetry between the two halves. Also black and white strongly dual, and then night and day is also showing up in here, and that's the title, day and night. Right? So keep your eyes open for duality. So that's one topic we cover, which we're not going to do today. Another thing we cover in the course is non-Euclidean geometry, which is probably the hardest math part. So Escher did not a whole lot, but a number of works that involve non-Euclidean geometry, either geometry on the surface of a sphere, or in this case, this print, Heaven and Hell, is geometry in hyperbolic space, which is sort of an abstract mathematical idea that was developed in the late 1800s by Lobachevsky and Poincaré. And it's a model of a geometry that doesn't satisfy Euclid's parallel postulate. So there can be more than one line parallel to another line that pass through a point. So we use this print and a few others of Escher's to jump off for that. Again, it's also a tessellation. The angels and devils in this fit together to fill out this disk. And you also see this theme of duality once again. Duality between black and white, and also, of course, good and evil. All right. So the main thing that I wanted to talk about today is this notion of art as illusion. Let's take a look at this print of Escher's on the right. And so what do we see in this print? Right. I'm asking the audience, can we get answers? Right. Take a look at balcony here. Right. And what do you see? An odd building. Okay. Thanks, Betty. Right. So it certainly appears to be a picture of a city. So what's odd about it is this bulge in the middle. Yeah, there's some sort of a fisheye look here. And indeed, it's a pregnant building. In fact, actually, if you have a really high quality picture of this, you can see that this plant in the middle may look like a hemp plant, and so it's been adopted by the sort of popular druggie culture. But that was not Escher's intention at all. But he certainly was popular in the sort of tripping era of the late 60s, early 70s. But what we see here is on the surface it is a picture of a city with a strange bulge in the middle. But let me read you this quote of Escher's, which didn't wrap for some reason on the slide, so I'm going to have to read it to you. What Escher says about this print is this. He says, "We sometimes forget that we are by no means dealing here with a city, but with a sheet of paper. You are not willing to accept this? The dream vision is dearer to you? Then I will rudely destroy it by making a bulge in the sheet." So what Escher's saying about this print is that you look at it and you see a city, but he doesn't want you to see a city. He wants you to see a piece of paper with a city printed on it. And how he's going to make you see that is by putting a bulge in the middle. So you realize you're not looking at a city. You're looking at, yes, it's easy done in Photoshop. That's true. Most of Escher's work is much easier done now with computers. And if you search the web, you'll see many people have. But in any case, the point he's making here is that this picture he's drawn is an illusion. It's not a city, it's an illusion of a city. So balcony's from 1945, and this certainly he wasn't the first artist to make this point. I think the most famous example is down here on the left. This is René Magritte's The Treachery of Images. It says, "Ceci n'est pas une pipe," which, if you speak French, you know, means this is not a pipe. So Magritte, in no uncertain terms, is telling you he has not produced a pipe, he's produced a picture of a pipe. So that's the theme we're going to look for today in Escher's work. So I want to take you on a little sort of historical tour of how art presents this illusion of depth. So we're going back in time quite a ways here to take a look at two historical images. And the question I want to ask here is, how does the artist in these pictures present his scene as a three-dimensional scene on a flat surface? How do you know which things are closer, which things are further? So let's look at the tomb of Khnumhotep, which is quite old, many thousands of years old. And already you can tell which things are in the foreground and which things are in the background. So what is it in this picture that lets you know, say, which man and which oryx, those are oryxes, which oryx is in the front? Right? So Marge says layering. Right? So layering in the sense that, especially right here, you can see that the horns of this oryx, which I can call the front oryx because we all sort of agree, they overlap the back one. Right? So that gives you the sense that there is a front layer which must be obscuring this back layer. So from this picture you can tell that the lower man and oryx are in the front and the higher one are in the back. And we see the same sort of thing in the 3,000 years later in this medieval period illustration from the Book of Otto. There's certainly, if you look here, the bowl that the person is holding is overlapping the one with the wreath. And so you know that bowl must be in front of her. Yes, okay. There's one more thing that's sort of subtle going on in these two images. And it's most obvious, I'd say, right there at the foot of Christ in this picture. Which is that in this box that he's sitting on, the back of the box is higher. It's higher up in the picture than the front of the box. Right? So Kelsey says perspective view. I wouldn't go quite that far yet. This is a very crude perspective in the sense that all they've done is put things higher in the picture. And we'll contrast this with the sort of true Renaissance perspective in a minute. And you can see that even in the Egyptian one, there's sort of a ground line, which I'm going to try and draw on here, right about there. Can you all see that ground line? There's a ground line which I'll call them the back man and oryx, although they're not, there's nothing back about them, everything's on the same picture. But the ones that we perceive as being in the back are slightly higher up. Their floor is a little bit higher than the floor of the two in front. And that's certainly true in the Book of Otto as well, in that box. And also there's a slight indication of it where the feet of the characters raise as they go upward. So now let's move forward a little bit in time to the Renaissance. Here's a couple of Renaissance paintings. And in the one on the left, St. Mark writing, right, which is early Renaissance, again we see that things that are further back in the image are higher up. So there's a box that sort of a pedestal that St. Mark is sitting on, and the back side of the pedestal here is higher up in the picture than the front side. What I also like about this is this attempt at a checkerboard floor, which to a modern viewer looks sort of messed up and wrong, but was really a triumph at the time. And again, they have not, at this point in history, worked out the sort of mathematics of linear perspective. But there is a notion that these lines that are further back on the floor are higher up in the frame than the lines that are closer. And not only that, but the lines that run away from the viewer, which I'll draw one on here, this guy, right? They're actually converging somewhat towards a point in the scene. Right? By Da Vinci's time, the mathematics of this had been well worked out, and so this very famous Last Supper of Da Vinci's has a strongly linear perspective on it, where the lines that define lines in the three-dimensional scene run away from the viewer. They all, if you follow the ones on the ceiling as well, they all converge sort of precisely to a point in the picture, and he's used it for effect to focus your vision on Christ in the center. And the other thing you'll notice about these lines that I've pointed out, these lines are receding directly away from us in this imaginary 3D scene. And they converge to a point on a horizontal line, which almost tautologically is known as the horizon. So all horizontal lines in this picture converge to a point on the horizon. So here's Escher's attempt to show you how you can do depth. This picture is actually called depth. It's almost a study. So how is he showing depth in this? How's he showing depth in this image? Right. So I'll open it up for questions. What techniques is he using so that you know which fish are in front and which are in back? Certainly overlap is one, and it's probably the strongest. So size is another. Good comment. Right. The ones that we perceive as being in the front are much larger than the ones that we perceive as being in the back. Right. Again, yes, there's receding lines. Thanks, Jim. Right. Horizontal lines that run away from us are rising in the picture. There's a fog in the back. Thanks, Veronica. The ones in front are much more detailed and darker. We're certainly seeing color used here. So yeah, density of print. So this is Escher's sort of study of all the different ways that you can show somebody what is in front and what's in back. He's trying to make an effective illusion of depth as possible. All right. Let me say something a little bit specific about vanishing points, because this is something Escher was particularly fond of messing with. So here's a very small image of the Tower of Babel, which Escher printed. It's a very early work, 1928, so it's not one of his well-known pieces at all. But even when he was getting started as an artist around this time, he was messing around with perspective. So he hadn't done anything impossible or weird yet, and yet he drew this. He made this print of the Tower of Babel in this striking sort of three-point perspective. There's two main sets of horizontal lines in this figure. This set, which runs parallel to the ground and off to our right, and they converge to a vanishing point on the right. And this set, which converge to a vanishing point on the left as they run away to us on the left. Since those are horizontal lines in the scene, they converge to vanishing points on a horizon line. And since the horizon line in this image is way above the top of the picture, it gives you a sense that your eye, which should be at the horizon level, that your eye is high above this tower. The other thing he does in Tower of Babel here is that his vertical lines also converge to a vanishing point. So the verticals in this figure are all converging as they run away from the eye, which is high above the tower. As they run away, they converge down to this point below the image called a nadir. So this has two types of vanishing points: horizon vanishing points and also a nadir. And if you look from the ground up at a high building, you also can have the perception that the verticals converge to a point above a building called a zenith. So here's Escher's other world, and he's making a point in this scene that these vanishing point constructions are completely artificial, and so what he's done in this scene is he's cut it into three parts, and there's a single vanishing point in the scene right about here in the middle. Actually, let me make a little dot on it. Can I make a dot? No, that's okay. I'm not going to mess around. So there's a single vanishing point in the middle, and in this part of the scene over here, that's used as a single point horizon vanishing point. Then in this sector of the scene, he's used it as a nadir. So in this part, vertical lines are converging to the same vanishing point that we had as a horizon before. And in this part of the scene, he's used it as a zenith. So in this case, upward parallel lines converge to this vanishing point in the middle. So he's using one vanishing point for three different purposes in the same scene. Interestingly enough, all three parts of it are actually representations of more or less the same picture. There's this man-bird sculpture and a horn with space in the background. So I'm not sure this is Escher's most effective play on vanishing points. He probably would agree. So let me show you one of his more sort of mature vanishing point works. So this is House of Stairs. And what he's got going in House of Stairs is the same thing he had in the previous one, vanishing points being used for different purposes. So I want to point out how this happens in this picture. So let me focus you on this curl up right here. And let's figure out which way that curl up thinks up is going to be. So if you look around the curl up there, that curl up would agree that this direction is more or less up. And this edge of wall, for him, looks like an upward line. So I'm going to trace that line and see where it goes. And if you follow it, that line that this curl up here thinks of as up converges to this point. So there's a point right here that is serving as a zenith for this curl up in this picture. Now let me call attention to another curl up. Let's pick U. Right. From this curl up's point of view, this line right here is the floor, and that's a horizontal line. And so this curl up would tell you that this horizontal line right here is also heading out towards this vanishing point, right? And so is this one. And so this curl up sees the same vanishing point as a horizon. So I'll make a little H next to him. Right. So we've got the same vanishing point used as zenith and the horizon in this scene. And here's a third one. This guy. And this curl up would agree that this line right here, and this line right here, and this, are all downward. They're all pointing downward. So from this curl up's point of view, these are parallel lines that are descending in the scene. And again, if you follow them, and they're not so clearly drawn, but if you follow them, they're constructed to also converge to the same vanishing point. So he's built a scene using one vanishing point in three ways. And unlike the previous slide where he had to make three separate scenes, at this point he'd figured out how to tie them all together to work into one single scene. And sort of the secret that he had to do this was to bend them. So in particular, this yellow guy's vertical lines, they curve back downward. And there's another vanishing point. Oh, there's another vanishing point. Where did it go? It's actually below and off the scene down here. There's a second vanishing point down here where the downward verticals for the yellow curl up converge to a zenith. And in fact, the whole picture you can see repeats about this much of the picture repeats again down here at the bottom. And in fact, you could repeat this picture and make an infinite strip. All right, questions about, yeah, I'm looking for questions. If you type them, I'll see them. Okay, let's see. All right, so here's a slide that did not work at all. So I want to introduce this notion of flatness. All right. So this is reptiles. At least this is some of reptiles. The rest of it didn't quite make the cut. Again, this is one of his more famous prints. So now we're moving on to a new topic of flatness. What's Escher doing in this scene? So there's certainly a sense of motion to it. We have some sort of reptile, some kind of alligator figure that is sort of crawling out of a flat page, climbing on a book, hopping up on top of a dodecahedron where it gives a little snort of power, and then crawling its way back into anonymity as part of a flat sketchbook tessellation. So one of the, do people see reptiles on the screen right now? Wolf in the Night does not. Okay, people do. All right, Wolf in the Night, you are having technical problems that are yours alone, I'm afraid. But you know what? Go type Escher reptiles into your favorite web browser, and you will see this picture. Okay. So again, Escher's trying to make this point that that his art, that the three-dimensional image that your brain reconstructs, is purely illusion. Not only that, but he can show you a flat scene transitioning into a 3D scene, even though all of the picture is flat. I wanted to show you another one here. Yeah, maybe not. Okay, we'll move on. But I definitely want to show you three spheres. So let me load this up. Oh, nice. Okay. Hopefully everybody can see Escher's three spheres. If not, you'll have to go searching for it. Okay. So Escher calls this three spheres. Why do you think he calls it three spheres? It's not a rhetorical question. I'm hoping people will answer. Right. So when you look at this, I think, okay, duh, maybe it was a rhetorical question. What your brain sees immediately is that there are three spheres, except something's wrong with two of them. Right? Some of them, there's something distorted about two of them. Right? So this top sphere, this top, I'm not even going to deign to call it a sphere, this top pattern of black and white on the page is almost impossible not to turn into a sphere in your mind. Right? He's given you sort of standard depth cues for something being a sphere. It's lighter on one side where presumably this imaginary light is coming from, darker on the other, and he's got a grid of curving lines that you can imagine would be circles and form a sphere. And then you look down at the next one, and it's sort of mysterious what's going on. And then the bottom one is maybe a little easier to reconcile. And I think what Escher is trying to get you to see here is that this one appears kind of flat. Right? This bottom sphere appears to be somewhat flat. Certainly, there's something wrong with the perspective as bulging anymore. But as Joyce says, it looks like a disk. So maybe this bottom one is a disk with a sphere pattern printed on top of it, or flattened, or something. So Escher is showing you, oh look, up here, this pattern looks like a sphere. Down here, it looks flat. And in the middle, he's done a sort of a mix of the two. So I'm going to draw a straight line on there. Right? And this straight line transitions between the top and the bottom. Right? The top sphere, which appears to bulge, is the bottom half of this middle sphere. And the top half of the middle sphere matches with the flat one at the bottom. So he's at least forcing you, whether or not you agree with this interpretation, he's at least forcing you to think about how your mind is creating these into three-dimensional objects. Right? And so Bruno Ernst, who was one of Escher's friends and another well-known artist, interprets three spheres as this. So he made this this is a picture Bruno Ernst drew to try and explain three spheres. And his explanation for it is that it's not three spheres at all. Right? The title is a total joke. There's no spheres in the picture, and what you're seeing is three patterns, which you could potentially interpret as flat objects with pictures of spheres printed on them. So this is, I think, a little game that Escher's playing. You look at his prints, you say, ah, it's a sphere, and Escher says, no, no, it's not a sphere. It is a flat piece of paper with ink on it, and you must accept it, right? With Balcony, he says he will force you to discard your illusions of three-dimensionality. So one technique he's used is vanishing points. A second one is flatness. Right? And the third one is this notion of ambiguous figures. Right? So I'm going to try and get the picture up here. Okay. I pretty much completely covered the text. Right? But this is the Necker cube. It was first studied by a psychologist whose first name I actually don't know, Necker, in the early 1800s. And so, again, what this is a pattern of lines on your screen. Hopefully, it is a pattern of lines on your screen if your technical issues are working out. It's a pattern of lines on your screen, which your brain almost can't help reconstructing into a cube. And an interesting thing about this is that there's really two ways that people reconstruct this into a cube. So I'm going to take a little poll. Hey, we even have enough people in the room to poll. That's good. So how many people see that blue dot as being very close to us in this cube? Raise your hand or click yes over there. You can. Right? The blue dot is close. Right? Right. So certainly you should be able to switch it back and forth between being the closest point of the cube and the furthest point on the cube. Although one of the interesting things to do as a psychologist studying this is to try and figure out sort of whether humans have a preference for one or the other. But you should be able to switch. And if you can't switch, there's a link on this page, which I've just covered up, to a really wonderful little applet that I'll just post a link in the chat session here. So I highly recommend that as you go and look at the Necker cube, that you click on this applet, because what it'll do is force you to continually switch back and forth between the two interpretations. Now, what's sort of psychologically interesting about the Necker cube is that although you can interpret it with the blue point in the front and the blue point in the back, the one thing that you will never do naturally is you will never interpret this line as crossing in front of the black one, as I've drawn it, while at the same time observing this line as crossing in front of the vertical one. That just isn't something your brain will do. On the other hand, you can certainly draw such a picture. So here's a very nice sort of almost photorealistic rendition of such a thing. It's called an impossible cube. So in this impossible cube, the artist has done exactly that. They've put this bar crossing in front and this bar crossing in front, which is not something your brain can naturally do. And in fact, it's not something that you could construct in 3 dimensions. Although people have a really fun time trying. If you go looking for real constructed impossible cubes, people have made many efforts to build such things. So what's wrong with the impossible cube is that the depth Q in this part of the figure, right, and it's the strongest depth Q there is, overlapping, tells you that the vertical bar is in front of the horizontal one. And if you follow that vertical bar upward, right, it tells you that this horizontal bar should be in front of the back one, but we have a very strong depth cue here as well, overlap, which says that no, the vertical bar here is in back of the horizontal. So there's really only two problems with this cube, here and here, and both of them would actually be perfectly acceptable by themselves. But taken together, they conflict and produce a figure that's impossible in 3 dimensions. Let me show you Escher's version of this. All right. So this is Escher's Belvedere. Right. And there's many, many things wrong with this figure, and all of them are based around the same principles as the impossible cube. That by overlapping parts of the figure, he can tell you what's in front and what's in back, and then force conflicts between them. So if you focus on this man climbing the ladder, right, because he's overlapped by the pillar, we know he's behind it. And as he climbs the ladder, now he's overlapping, or I guess it's a different man, as the jester at top of the ladder is now overlapping the house. We know he's outside the house. Right. He's done a similar thing with the pillars all over this picture, where he takes a pillar that apparently, because of overlapping, starts at the back of the house and draws it downward to connect it up to part of, because of overlapping, what we know is the front of the house. They also point out down here in the corner, there's a little guy holding an impossible cube and looking at a picture on the ground of a Necker cube. Right. So maybe the most impossible or classic of the impossible figures is the Penrose triangle. I've got a picture here of a Penrose triangle. It's got 3 pieces, all of which are perfectly acceptable figures. So there's 3 corners to this. And if you focus on any one of the corners, it's a perfectly normal picture. In fact, you can take any 2 of these corners. So take your thumb and cover up any one of the corners, and you get a perfectly reasonable geometric object. So it's only when we go around in this circle that the depth cues in the 3 corners conflict. This was created by Oscar Reuterswärd in 1934. He's a Finnish artist, maybe no, Swedish artist. And he has a wonderful collection of impossible figures. I had one of his original impossible triangles over here on the right, but it's gone. So you'll have to go check him on the web afterwards. Sort of sadly, it's not called the Reuterswärd triangle, it's called the Penrose triangle, because the mathematician Roger Penrose was the one who really brought it to the popular consciousness. And he, in fact, is the one who introduced it to Escher. So here's Escher's use of the impossible triangle. It's a maybe his most famous print, waterfall. And what he's got here is a figure that, again, if you focus on small parts of it, is quite a reasonable 3D image. So in this section over here, if you just focus on that, what you see is water. And it's a little bit hard to see, but if you just focus very carefully on this section, you can see that the water is flowing down. Right? The edges of the trough that the water is in, they step down as it moves along. And then we come to another corner, and the water continues to flow downhill if you just focus on this section right here. Again, if you look at the edges of the trough, they are stepping down as the water flows. So locally, at least, this water is flowing down. But you can already see that by having gone around this corner, it's done 2 of 3 sides of an impossible triangle. There's the 3rd side. Right. And so even though the water has flowed downhill locally, it's conflicting with depth cues that tell you it is somehow higher and directly above where it was before. So there's one sort of impossible triangle built into this figure. Do you know how to erase? No, it's okay. We'll just survive. So there's two more impossible figures, impossible triangles in this figure. There's one of them here, and then those have joined together and share sides with yet another one here. So he's constructed this water which flows downhill everywhere, and yet seems to be a cycle out of three sort of connected impossible triangles. All right. Okay. Another source of ambiguity can come from shading. So I have two copies of the same figure here with dots. And in one figure, you'll notice that the sort of H-shaped pattern of dots, or maybe I-shaped pattern of dots, on the left, I would imagine almost everybody sees those as dented in, and the other ones as pushing out. Right? So these guys are dented in, and these ones push out. Over here we have the same figure flipped upside down. So it's the same picture. So these dots here are the same ones you used to see as dented in, and now possibly you see them as bulging out. If you work at it, you should be able to get them to flip. But instinctively, you do have a preference between them, and that's because in one of these figures, in order for now I can't even see which one's which. Okay, this one, these dots, which should be bulging out, if they were bulging out, they'd be illuminated from above. Whereas in this figure, this dot, in order to bulge out, is illuminated from below. So although you should be able to switch on these with a little effort, people do tend to prefer illumination from above because that's usually where the sun is. And then down here I have Escher's cube with magic ribbons, which is cut off. I think in the interest of time, I'll let you go see that on the web page. Because I did want to finish with convex and concave, which we don't have. All right. So this is convex and concave, and this is a print which is perfectly normal on its left half and perfectly normal on its right half. So your exercise that you need to do here is to cover up, say, the right half of the figure. Right? So get a piece of paper or your hand, or if you're using a projector in a classroom, then, I don't know, a hold of a desk or something. But focus on the left half of the figure for a moment. And what we have here is a lady. I haven't done anything to draw on it yet, so if you're just getting it now. On the left half of the figure, there's a woman walking across a bridge who will descend some stairs down to a platform where a man is sitting. That man could walk into this room, right, and maybe meet with this guy who's climbing up the stairs. This man also, if he walked over here, would have to be very careful because there is a very steep cliff right there that he might fall off. And you know it's a steep cliff because there's a rope hanging down below it. So this picture is full of visual clues. A window with a plant in it. A trumpeter sticking his head through a window. If he were to step out of the window, he would be on this roof. So it's full of depth clues, overlapping, shading, light and dark, right, that tell you that these are stairs that this woman could walk down. Now, if you're with me still, cover the left half of the figure, and let's focus over here. I find people have a harder time with the right half. So what we see here is a man climbing a ladder, and he could step onto a platform here. Right. He could walk out through this door. He could walk out through this door. Right. But he has to be very careful not to step off his platform, or he will fall down to the abyss below. And Escher's given you a rope here to help you see that. And this rope is attached to this surface, which must be a ceiling. Right? This surface right here is a ceiling. And you know it's a ceiling because there's a pot hanging from it. And here's the underside of some stairs. And if you can see this is the underside of some stairs, you've succeeded in reading convex and concave properly. That underside of stairs leads to an underside of an arch where a flag has been attached and hangs down. And you can see this man sticking his head out the window with a trumpet. And if he falls, he has to be careful because there's nothing below him. Now when you bring the two together, those two halves are completely in conflict. This man sees this as a floor. The pot sees it as a ceiling. And you can't reconcile along this middle line, the left half of the figure, which you might think of as the convex half, and the right half, which you might figure as concave. So this one takes some time, I think, to really get used to it. You should be able to flip the left half to be convex and the right half to be concave if you work at it hard enough. All right, I'm going to switch to just say that if you want to learn more about this, we have a free and available online textbook for our course at math.slu.edu/Escher. Another, probably the finest source for this sort of information is a book by Bruno Ernst called The Magic Mirror of MC Escher. It's out of print, but still not so hard to get. So if you're looking for that, looking for more information, that's highly recommended. So I'm going to drop back to convex and concave and maybe stop talking and take some questions.
So if you have a headset, the microphone is open, or if you want to type in your question, you can. I'm actually going to stop the recording now, though, so we can just do an informal chat.